Good morning, friends. Today we are going to discuss another important law in electrical engineering, Kirchhoff's laws. Kirchhoff's laws were formulated by Gustav Kirchhoff in 1845. There are two laws, one for current and other for voltage. They are known as Kirchhoff's current law and Kirchhoff's voltage law. Let us consider first Kirchhoff's voltage law, which states about all the currents that meet at a point, a node, or a junction in a given electric circuit. It states that the algebraic sum of currents meeting at a junction in an electric circuit is 0, or alternatively it can be stated as total incoming current is equal to total outgoing current at any junction in an electric circuit. To explain this, let us consider an arbitrary junction from an electric circuit. So we see that four currents I1, I2, I3 and I4 are meeting at the given junction. As we see, currents I1 and I2 are directed towards the junction, whereas currents I3 and I4 are directed away from the junction. So according to law, so as to take the algebraic sum, we have to decide some sign convention for incoming currents and outgoing currents. Suppose we consider the incoming currents as positive, then outgoing currents will be negative. Similarly, if we consider the outgoing currents as positive, then incoming currents will be negative. Thus, applying the Kirchhoff's current law at given junction, total incoming current is I1 plus I2, whereas total outgoing current is I3 plus I4. So according to law, the total incoming current should be equal to total outgoing current. Now let us consider one example which explains the use of Kirchhoff's current law to find out the unknown current. Considering the same junction wherein I1 is given as 2 amperes, I2 is given as 3 amperes, I3 given as 4 amperes, while I4 is the unknown current to be found out. So applying the Kirchhoff's current law at this junction, it is plus 2 ampere, plus 3 ampere, minus 4 ampere and minus I4 should be equal to 0, which gives I4 is equal to 1 ampere. So this was about the Kirchhoff's current law. Now let us discuss Kirchhoff's voltage law. Kirchhoff's voltage law is stated over a closed path in an electric circuit, which is also called a loop. It states this way: the algebraic sum of voltages around a closed loop in an electric circuit is 0, or alternatively it can be stated as the total voltage rise is equal to total voltage drop around a closed loop in an electric circuit. So as to understand this, let us consider first the sign convention as we did in case of Kirchhoff's current law. For any element the voltage has polarities positive and negative. If we are traveling from positive to negative, we will consider this as positive voltage, whereas if we are traveling from negative to positive, we will consider it as negative. We can try the opposite convention also, that does not matter, but that should be followed throughout the problem. So consider now an arbitrary closed loop which consists of 4 elements and voltage across them as V1, V2, V3 and V4. This forms a closed loop, that is, starting from A, if we travel through V1, V2, V3 and V4, we return to point A. This forms a closed path or closed loop, and the voltage law is always stated over the closed loop. Now applying the Kirchhoff's voltage law to this loop and starting from A, following the convention stated here, we can write the KVL equation, Kirchhoff's voltage law equation, for the loop traveling in clockwise direction as from A, it's first V1, as we are traveling from negative to positive, it's minus V1. From this point, it's minus V2 because we are traveling from negative to positive again. Then it is plus V4 as we are traveling from positive to negative, and with the same reason we have plus V3, and the algebraic sum should be 0. Instead, if we travel in clockwise direction starting from same point A, it would be minus V3 minus V4 plus V2 and plus V1 is equal to 0. Result will be the same though we travel in clockwise direction or anti-clockwise direction. Now let us consider one example wherein we find the unknown voltage between any 2 points. Let us consider first to find out the voltage VAD. Here is the point A and here is the point D. So to find out VA to D, we start from A to D, it is VAD. Since we are considering this as positive, this as negative, so VAD will be positive. Next, from D to E, we are traveling from positive to negative, so it is plus 30. From E to F, we are traveling from negative to positive, it is minus 15, and for same reason F to A is minus 5. So this gives a complete closed path from A to D, traveling via E, F and A, and therefore sum should be 0. So this gives VAD is equal to minus 10. Next, let's find out VFC. Here is the point F and here is the point C. Let us consider VF, F point at positive and C at negative. So with this, VFC will be positive. From C to D, it's minus 12. From D to E, it's plus 30, and E to F is minus 15. So this forms a complete closed path and sum should be 0. So this gives VFC is equal to minus 3 volt. So this is how we can find the unknown voltage. Alternatively, we can find this VAD by traveling through A, B, C, D and A, another closed path, or VFC by F, A, B, C, F. Result will be the same. Applying Kirchhoff's law, we will get VAD is equal to minus 10 volt and VFC is equal to minus 3 volt. So this is how to find out the unknown voltages in a single loop closed circuit. So in next class we will consider more complex problems of finding the voltages and currents in multiple loop electric circuits.